Welcome back. In our last explainer, we talked about how the linker is kind of like an architect, creating this really detailed blueprint for our program. Well, today, we're leaving the drawing board and heading straight to the construction site. We're going to build a solid, practical mental model of how memory actually works in an embedded system. All right, let's get into it.
So that brings us to the big question for today. The linker makes all these plans, right? It says where the code goes, where the data goes. But where do these sections physically live? Where's the foundation poured, and where does all the day-to-day work happen? To answer that, we first need to understand the two fundamental building materials we have to work with.
And those two materials are flash memory and RAM. These are the actual physical chips on your microcontroller that give your program a place to exist. Now, they both store information, but they have completely different jobs. And I gotta tell you, understanding that difference is absolutely one of the keys to becoming a really effective embedded engineer.
The main trade-off here is pretty simple, but it's incredibly important. Flash is what we call non-volatile. That just means it remembers everything even when you unplug the device. Think of it like a hard drive. It's for long-term permanent storage. RAM, on the other hand, is volatile. The second the power goes out, poof, it forgets everything. It's the fast, temporary workspace.
So let's take a closer look at flash. Because it's non-volatile, it's the absolute perfect place to store the firmware itself. When you hear someone say they're flashing or programming their microcontroller, what they're doing is writing the compiled code, all the constants, maybe a bootloader, right into this permanent memory. It's the forever home for your program's instructions.
And then we've got RAM. Now, RAM is incredibly fast to read from and write to, so it serves as the active workshop for our program. This is where all the action happens when your code is actually running. All your variables, your data buffers, the stack, the heap, all the stuff that changes minute by minute while the program is executing, it all lives here in RAM. And this brings us to what is maybe the most crucial distinction of all. Your program is permanently stored in flash, almost like a set of instructions locked away in a safe. But when you power the device on, the program lives and runs in RAM, using it as this dynamic, high-speed workspace to actually get things done. Okay, so now that we have our physical foundation of flash and RAM, how does the linker actually organize all the different parts of our program? The code, the constants, the variables across this landscape? Well, it does this by using standardized memory sections. And when you look at it, this layout is actually incredibly logical. The .text section, that's your actual machine code, your instructions. That gets stored in flash. Same thing for .rodata, that's your read-only data. And this is where the C language really meets the hardware. When you declare a variable as const, you're basically telling the linker, hey, this thing never changes, so go ahead and stick it in the .rodata section, where it can live permanently and safely in flash. Now look at .data and .bss. These are for your global and static variables, and they both live in RAM. The difference? .data is for variables that have an initial value, which actually gets copied from flash at startup. .bss is for uninitialized variables, which just get wiped to 0 in RAM when the device powers on. Now, inside that block of RAM, things get even more interesting, because we usually have two very dynamic regions. Let's start with the stack. The easiest way to think about the stack is as an incredibly efficient, totally automatic workspace that the CPU uses to manage function calls. A lot of the time, this happens without you even having to think about it. Here's the play-by-play. When your code calls a function, the system automatically pushes its arguments and the return address onto the stack. Then it carves out a little space for any local variables inside that function. The function runs, does its thing, and when it's done, all of that space is automatically cleaned up and reclaimed. It's a last-in, first-out process, or LIFO. Super fast and super predictable. But, and this is a huge but, that awesome efficiency comes with a major risk. The stack has a fixed size. If you have way too many nested function calls, or maybe some really big local variables, you can literally run out of space. This is a stack overflow. And in an embedded system where there's no operating system to catch you, it's absolutely catastrophic. It leads to memory corruption and these weird, unpredictable crashes that can be a total nightmare to debug. Now, the other dynamic region in RAM is the heap, and unlike the totally automatic stack, the heap is for manual, on-demand memory allocation. So when your program needs a chunk of memory while it's running, and you just don't know the exact size when you're compiling it, you can ask for it from the heap using functions like malloc. However, in the world of high-reliability embedded systems, the heap is often seen as a pretty big liability. Why? Well, because manual management can easily lead to memory leaks if you forget to free every single thing you've allocate. It can also cause memory fragmentation over time, making it harder and harder to find a big enough chunk of free memory. And most critically for real-time systems, the time it takes to allocate memory is non-deterministic. It's unpredictable, and unpredictability is poison for systems that have to respond on a dime. So let's just put them side by side. The stack is automatic, it's fast, it's predictable, and it's highly reliable. The heap is manual, it's slower, it's non-deterministic, and it carries some pretty significant risks. This is a fundamental trade-off that every single embedded engineer has to think about. For a lot of industrial, medical, or safety-critical applications, the risk of using the heap is just way too high. So, what does this all mean for us? It means that developing for an embedded system requires a completely different mindset than, say, developing for a PC. You're not just writing algorithms in a vacuum. You are actively managing finite physical resources. You are always working within strict constraints. Your flash is not infinite, so your code size really matters. Your RAM is precious, so every single variable counts. You have to carefully think about your maximum stack depth to make sure you never have an overflow. And you have to treat the heap not as some convenient tool, but as a potential liability that needs a very strong justification. Memory isn't abstract, it's your primary engineering constraint. This next idea really just captures the essence of everything we've talked about. Writing embedded code isn't just about making an algorithm on a screen. It's about designing machine behavior. You are directly telling a physical device how it's going to act in the real world, and you're doing it under the strict rules of limited memory and real time. That's a huge responsibility, but honestly, it's also what makes this field so incredibly cool. So we've built a pretty solid map of our memory now. We know that .text is in Flash, and .data and .bss are in RAM. But that leaves one final burning question. If those .data variables live in RAM, but their initial values are stored permanently in Flash, how do they get there? What kind of magic happens between the moment you apply power and the very first line of your main function? Well, that is exactly what we're going to uncover in our next explainer when we dive into the critical role of startup code. I'll see you then.